All right, let's go ahead and talk about chemical bonding. So, the three main types of chemical bonds are as follows. You have first, ionic bonds. That is the force that holds oppositely charged ions together, forming formula units that come together to form crystals. So, a common example of this one would be table salt, which is NaCl. So, that is held together by an ionic bond. Metallic bonds are the force between metal cations and the valence electrons surrounding them to form a lattice-like structure. So this is what holds metal alloys together, for example. And then lastly, we have covalent bonds. That is the force that holds two nonmetal atoms together via the sharing of electrons to form molecules. And this would create things like glucose, which is C6H12O6. And those are all nonmetals. Okay, so let's talk more about each of these. Again, ionic bonds. We've got this example of table salt, which is sodium chloride. So this is the formula for it, NaCl, just one of each. And that is because this positive charge on the sodium is attracted to the negative charge on the chloride ion, and it makes this lattice-like structure. It's very rigid in its structure, and it's a crystalline shape. Okay, and that's why ionic salts, for example, have this crystal lattice structure. Okay, so that's how those are formed, and it is via the transfer of electrons. So sodium, for example, has one valence electron. Chlorine has 7 because it is a halogen. It's in group 17. The sodium will transfer its electron directly over to chlorine, making sodium have a positive charge and chlorine a negative charge, and that is what attracts them together. All right, so that's ionic bonds in a nutshell. What about metallic bonds? Metallic bonds are a little different. We have silver here, silver atoms surrounded by electrons. Okay, these would be the electrons that silver brings in, and it's sort of known as a sea of electrons. Okay, that's how most people think of this. Metallic bonds, they sort of share their electrons throughout, but they're not filling valence shells in particular. They're sort of just moving around, and that's what gives metals their metallic characteristics as well. They conduct electricity very well because electrons can just pass right through and carry their charge. All right, so that's metallic bonds. And covalent bonds are the last one. That would be the sharing. Okay, so covalent. Co would mean sharing, and valent obviously has to do with the valence electrons. The goal here is to achieve a set of 8 valence electrons, except for the case with hydrogen, which only needs 2 because it is in the first period of the periodic table. So here's an example. Each fluorine atom has 7 valence electrons. A covalent bond completes the octet for both. So as you can see, fluorine is missing one here and here, but if they were to share these two, as you can see here, that would complete the octet for both. And that is the idea of covalent bonds. Another example would be forming water with hydrogen and oxygen. Hydrogen is lacking 1, and oxygen is lacking 2 because it has 6 valence electrons instead of 8. So you would need 2 hydrogens and 1 oxygen in a single covalent bond to share, and as you'll notice, each hydrogen has 2 and the oxygen has 8, and everything is happy. All right, everything is stable in this water molecule here, and that is covalent bonding. So that's just a general overview for the three main types of bonds. Okay, to understand this more, let's answer this question to understand this analogy. So, who would win in a tug of war between these two individuals? So, we've got a sumo wrestler and the wimpy kid. Obviously, the sumo wrestler would win. How about these two? Well, it's hard to say. It probably would end in a tie, correct? How about these two? Again, it would probably end in a tie because they're identical. So that's generally the idea behind this topic, and this is super important to understand. Electronegativity. So it deals with electrons, and electronegativity is the relative ability of an atom to attract bonding pairs of electrons to itself. So how strongly do these atoms pull electrons towards the nucleus? Okay. And we already talked about effective nuclear charge, right? In the previous unit. So go back and read those notes and try to understand that or ask me some questions about it. An atom that shares electrons with another atom behaves similarly. That is a key thing to understand. Those that win the tug of war, so to speak, for electrons are said to be more electronegative. So when we say something is more electronegative, it means that it's winning the tug of war. Okay? So here's another trend in the periodic table, and this is about electronegativity. It increases as you go up to the lower numbers of the periods, and it increases as you go to the right across the groups. Okay, and fluorine happens to be by far the most electronegative, and it decreases as you go here, which would lead you to believe that francium is the least electronegative. Okay. So here's a table of Pauling electronegativity values, and this is a special periodic table that has these values. You would not see this on a typical periodic table, but these tell you how strongly electrons are pulled to each of these atoms, right? So fluorine, like we said, has a value of 4.0, and it's the strongest. Francium down here has a value of 0.7. So as you can see, it generally increases right up to fluorine. Here's a question for you. Why do you think the noble gases have no value shown? So the noble gases are in group 18 here. Why do they not have any values? Well, it's because they have a full octet. Helium has its 2, and all the rest of them have 8 electrons, okay, in their valence shells. So they don't need to pull electrons to themselves, and they don't want to give up electrons either. They're perfectly content with the way they are. So we ignore those when we're talking about electronegativity for that reason. Let me show you how this works in general. It's pretty simple. So here's a little practice for you. I suggest you pause the video after I explain this and give this a try yourself. So determine the electronegativity value of each element in the bonds below, and then find the electronegativity difference between each atom in the bond. The electronegativity difference is always a positive value, so don't worry about positive and negative signs. So you can take the absolute value of these. Let me do the first one for you. So boron and chlorine. So let's locate these. Boron is right here, and chlorine is right here. So these values show how strong they are at pulling electrons to themselves. Let's give them a value. That's 2 and that's 3. The difference, of course, here would be 1. And that's really all there is to it. So just find the difference between the two values. I'll give you a moment to do that. Pause the video. and then press play and we'll talk about the answers. Okay, so hopefully you did that. What we have here is the electronegativity value difference. Okay, so we're concerned with just the difference between the two. Like we said, boron and chlorine has a value of 1 difference between two things that are the same or identical would be 0. So in this case, oxygen has a pretty high value, and that would be like a sumo wrestler against its identical sumo wrestler twin. And the process is the same for the rest of these. So beryllium and fluorine has a difference of 2.5, potassium and bromine has 2, carbon and hydrogen has 0.4, and so on. But what do these values mean? What is the point of finding these values? Well, a bond with an electronegativity difference of 1.7 or lower, okay, so X is going to be in this inequality, such as we can see here. If it's below or equal to 1.7, it's said to be covalent. Okay, and covalent means the sharing. So it's sharing electrons. For the problem above, decide whether each bond is ionic or covalent based upon the electronegativity differences. Okay, so let's go back to that previous page and look at a few of these. Okay, so we're looking at things that are less than or equal to 1.7 in their values. So let's just go ahead and circle those. So this is pretty easy to do. It looks like most of them are less than 1.7. Okay, so all of those, as you'll notice, are going to be nonmetals bonded to other nonmetals. Okay, and that is a key thing to understand. What this is saying is that no one fully outright wins the tug of war for the electrons, and so they have to share them. Okay, so they share them via covalent bond. And ionic bonds, on the flip side, are generally between metals and nonmetals. Okay, so that would be an electronegativity difference of where X is greater than 1.7. Okay, so that would include this one, and this one. And as you can see, those do contain a metal, nonmetal, metal, nonmetal, and a metal and a nonmetal. Okay, so covalent bonds are generally between two nonmetals, whereas ionic bonds that have an electronegativity difference of greater than 1.7, meaning the nonmetal wins the battle, the tug of war for the electrons. And that's between a metal and a nonmetal. So look at the table of electronegativity values. Do the statements make sense? And we just went over that, and they should make pretty good sense. Go back and review that and make sure that you can see the clear difference between covalent bonds and ionic bonds and the electronegativity difference cutoff between them. And it is 1.7. That is a number I would like you to remember.